Hi, scientists. Some of you are measuring energy, and some of you are interested in finding the uncertainty for energy. And I'm going to show you two ways to do that. One way is max minus min divided by 2, which we saw last year in grade 9 if you're with me. And another way with propagation with a formula. If your data, this is real student data, is set up like this, where you have initial temperature, and then final temperature, and then change in temperature, and then they use each change in temperature to find each energy and find the average energy, then we can find, I was going to color this, is what I added. We could add this column here, uncertainty energy produced. How we do that is already been shown to you in the lovely lab guide in this optional video here, using max minus min divided by 2. And the short formula I will show you and zoom in is you have the maximum of the things minus the minimum of the things divided by 2. So max of these three things minus the minimum of these things divided by 2 gets you that. Then you fill down and you get this. That's your uncertainty with one way. Now, if you've just done it and you have it in a different type of table, and at the end you have your energy produced in about the individual ones, we can just use a fairly simple formula, and I'm going to show you the working out for this. I've got the working out in this tab here. So the uncertainty in the energy is equal to the uncertainty of the mass of water heated divided by the mass of water heated plus the change in the uncertainty change in temperature divided by the change in temperature times the energy. So we're going to have the students' numbers. They had 30 milliliters of water, and if they measured it precisely with a measuring cylinder, they should have 30.00 milliliters, and that would give you 0.05 grams, because 1 milliliter is 1 gram of water. Now, this student did not measure temperature at all precisely. They have an uncertainty of temperature what? So they didn't have any, they just kind of barely read the thermometer. They didn't use like the 0.1s, the 0.2s. I don't know why not, but this is their real life data. So if they have an initial temperature, they have a final temperature, a change in temperature, because you have two separate things. You have uncertainty of one, and the other one, they add together. So they have an uncertainty of change in temperature of 2 degrees, and that's why I've got 2 degrees here. And their change in temperature is, let's say here, 7 degrees. So it's 7 degrees. And then you multiply by the actual energy that he already has of 840. So we have that. And I use my calculator. And this is actually quite interesting when you show you working out here. So there's uncertainty in the mass. And according to this calculation, oops, I should have a decimal right here. This is like 0.17%. And this is like 29%. If we multiply by 100, we get a percent. So you can see the change in temperature influences their uncertainty by 29%, and the mass only 0.17%. And when we type that in, oh, this is actually for the old value. That's not true anymore. It's 2, because I actually made a mistake. Then I fixed it. 252 joules. That is concerning the energy. So I take that, and I'm going to put this formula in the spreadsheet. So I'm going to delete these. And we can watch me type it in. Equals, what do I have here? Brackets. 0.05 for the uncertainty in the mass of the water. Not the mass of whatever was burning, popcorn or chips or almonds, whatever. It's really the mass of the water in the test tube. Divided by the mass of the water in the test tube. Plus the uncertainty in the temperature. The uncertainty in the temperature is 2 for this particular student, because they did not measure precisely at all. Yours should be like 0 point something, I think. Divided by the actual change in temperature. Is that number there? I close bracket. Then I multiply it by this, and hopefully I get 252. I got 253. And I fill down. That's good. They go up by 1, so this bothers me. Alright, so I'm just gonna check it. 0.05 divided by 3, it's always true. Plus 2 by the change in temperature. In this case, I want to do this one. 22 equals that times energy produced, 2730. I got 253 here, not 257. But again, it could be the rounding of weight has more decimal place inside here, so that's fine. Yeah, and see. Yeah. So that's right. It just, because they all go by 1, that kind of bothers me, but I checked it. The formula is right. It agrees with the calculator within rounding error, so that's okay. So now we go to Logger Pro, and we're going to put the uncertainties in. And this is a cool thing about Logger Pro, is you can actually have different uncertainties for each value. So what we need to do is just we go to experiment, or data, sorry, new manual column. I'm going to call this uncertainty in energy, delta E, this is in joules. We're going to put in these values here, let's copy them and paste them. Then I'm going to come to the mass, and the uncertainty in mass is 0.01. And the uncertainty for energy is not going to be one particular value, it changes. And we're going to use the column uncertainty in energy, and we'll get these huge error bars. So by doing this extra work, you can see the relative importance of the uncertainty in mass compared to the uncertainty in the heat energy. And by doing this calculation here, and showing your work at least one time, you actually see what part causes it. Is it this part or this part? And you can easily see the math here, which one causes it more. Hopefully this helps. Take care and enjoy.